Hey, what's up, guys? Okay, so in this video that we are going to talk about another results, which is called a triangle removal lemma. Okay, so previously I have already introduced the triangle counting lemma and the Zamaradi regularity lemma. So you can start from these two lemma and prove these weird results, very deep results for the triangle removal lemma. Okay. You can go Wikipedia and just type. You can see the what's the statement. Okay. So let me just write down. And okay. So maybe let me just give one motivation. So motivation. So motivation is that given a graph G, we want to ask we want to relate to property. One is the number of triangle in G. The second one is that the minimum edges that we need to remove to make G triangle free. Okay, so this question basically asks what's the 1 and 2, or what's the relation between 1 and 2. So relation, or basically scale. So the obvious question is that the obviously trivial facts that we know that 1 is less or equal to 1 greater or equal to 2, right? Because let's say we have like 100 triangle, then I can take every triangle and remove one edges, right? And this will make the graph triangle free. And another intuition is that if we can remove if there's a very small very little edges that we can remove, then we guess that the graph should not have a lot of triangle. Okay, so it's too small. This implies 1 is. Okay, but we want to know scale. Okay, we want to know scale. So what this means is that suppose that 1 is O(n) cube, or maybe then that's equal to that small O(n) cube. Okay, little O(n) cube, and we want to know that what's the max, what's 2, what can we say about 2? Can we make these can we make triangle free only remove like O(n) cube, O(n) square edges, or we need to like little O(n), we need to like n square log n, or whatever number of edges that we need to remove to make all the to relate the number of triangles to the minimum edges. Okay, so this triangle removal lemma tell this fact. Basically for L epsilon greater than 0, there's a delta greater than 0, which is a function of epsilon, such that for every graph with number of triangle less or equal to delta n cube triangle, then G can be made triangle free by removing at most epsilon n square edges. Simply speaking, is that if the number of triangle is little O(n) cube, then that G can be made triangle free by removing at most little O(n) square edges. Okay, you can think a little bit, and you will find that this theorem is very deep. It's not that it's a very non-trivial theorem, because it tells that if you remove O(n) square edges by some epsilon, there's always some fraction of triangle, n cube triangle, that you can remove. And this is for every graph G. So it's very universal. Okay, so in order to prove it, let me just quickly recall this triangle counting lemma, right? So this lemma says that if you have XYZ repair such that there are pairwise epsilon regular, then and also this edge density is greater or equal to 2 epsilon, then we know that the number of triangle between the XYZ part is at least greater or equal to 1 minus 2 epsilon, and dxy minus epsilon, dyz minus epsilon, and dxz minus epsilon times xy Okay, and these are a number of edges between x and y. So x, y, z, e. Okay, and Zamarati regularity lemma says the following. So for every graph G, or for every epsilon greater than 0, for any graph, there's a epsilon partition, epsilon regular partition. By at most little big O epsilon. So this means that it's depend on epsilon but constant. Okay, so it's big O. So big O1 depend on epsilon. So combine these two, then we can prove this triangle removal lemma. Okay, so let's go to the proof. Okay, so you start with some graph G and then you do partition. Okay, so the first one is that we do epsilon divided by 4 partition. Okay, the second one is that we remove some edges. We want to say if we remove these edges, then the remaining graph must be cannot have any triangle. Okay, so we remove irregular pair. So the first step is that we remove the irregular pair. Remove vi vj epsilon divided by 4 irregular pair. So vi vj, right? There's if these two guys are irregular, then we remove all the edges between them. Okay. The second one is that we remove low density pair. So if there's a dvi vj is that's equal to epsilon divided by 2, then we remove. Okay, so we remove all the edges. So if there are vi and vj, there are low density, few very small edges, then we remove them. Okay. And this finally we remove a small pair. A small pair. Sorry, small pair base or small part. Sorry. So small parts that we remove if you have any two pair, let's say vi, vj, right? And you have any pair, and if one of it is one of the density, let's say vi or vj, is less or equal to epsilon divided by 4m. So what's this m? This m is just the number of parts. So we just write b into b1 into up to vm. So these are partition. Notice that m is just all epsilon 1. So this means that there are m just constant depending on epsilon, but not the size of the graph. If there are low density pair, then we remove it. So if this is your vi and your vj are very, very small, there's no number, the edges are, the number of vertices are very small, then we remove all the edges between it. Okay, so remove these three, then claim is the following. The rest graph has no triangle. Okay, so before we prove this, let's count how many number of edges that we remove. Okay. So this guy is epsilon divided by 4 irregular, right? So the number of edges by definition is just epsilon, at most epsilon 4 divided by n squared. Okay. So n is the number of vertices. And the epsilon 2, right? You remove all the vi, vj with epsilon 2 edges, with epsilon divided by 2 edges, right? You remove all the density small pair. You remove all the pair with density between less or equal to epsilon divided by 2. So you at most remove epsilon divided by 2 n squared edges. Okay, right, because the density is at most epsilon divided by 2. Okay. Now you remove all the small parts, right? So you remove epsilon divided by 4m n squared. But you at most have m parts, right? You remove everything. So it's epsilon divided by at most epsilon divided by 4 n squared edges. So totally you remove epsilon n squared edges. Okay, so you remove at most epsilon n squared edges. Now I won't claim that the rest has no triangle. Okay. And the reason is the following, right? So suppose no, suppose not. Okay, suppose not. Okay, then suppose not, meaning that there's a repair, let's say x, y, z. Okay, this x, y, and z can be the same or distinct, right? But suppose not. Suppose not means something, right? Means that these two, we know that these are epsilon divided by 4. suppose not, right? Meaning that there is a triangle, right? So there is some triangle, some point here, and some point here. So they connected, they connected, they connected. Okay. Then by our results, then by our removing procedure, meaning that x and y are epsilon 4 divided by 4 regular, epsilon 4 divided by 4 regular, epsilon divided by 4 regular. And then we also know that dxy is greater or equal to epsilon divided by 2, right? By our construction, and the yz part is also epsilon divided by 2, and the xz part is also epsilon divided by 2. Okay. And then we also know something. We also know that they are large enough, right? So this means x and y and z are at least greater or equal to epsilon 4m. Okay. By so their density, right? So it's so they're at least epsilon n squared divided by 4m. Okay, right. So there are so these are I forget this NT because we'll count this is density. this is density. So I need to remove this word. This should be there some scale with NT. Okay, so okay, epsilon n divided by 4m. Okay, so if there's these edges connected, still connected, there are one triangle remaining. Okay, then the total number of triangle by the triangle counting lemma will greater or equal to 1 minus 2 epsilon divided 1 minus 2 epsilon. Now this is epsilon divided by 4 times the epsilon divided by 2 minus epsilon divided by 4, and the cube times xy times x times y times z. So it's epsilon divided by 4. Okay. So this means that there are some constant. Let's call this delta. Okay, delta n squared triangle. Okay, so what this means is the following. If there's a triangle remains, one triangle remains, then you show that there at least have delta n cube triangle. Okay, so suppose your original graph, suppose the original G has less than delta n cube triangle, then this cannot happen. Right? This cannot happen. Because I already removed some edges, but the number of triangle increased. Right, so it's contradiction. Okay, so this proves that if G originally has less than delta n cube triangle, then after the removing step, there should not have any triangle. Okay, so this proves the triangle removal. Okay, so this is the proof, and yeah, that's it. So next video we talk about application.